thank you for coming, even if this is getting to be the vacation period for Scandinavia. So I'm very happy to see many of you here. And thank you for inviting me, and I'm really looking forward to spend time here at KTH and interact with friends and fantastic students and postdocs. Okay, exactly because the host, I chose to try to make a point here about the use of digital twins in a practical application, and trying to match it with some fault detection and distributed diagnosis that I developed in the last few years and applied in a real industry case. Okay, I will try to make the point. I have a number of backup slides for the technicalities, but on I will not go into the details and trying to give the big picture. And then, of course, staying here for a while. I mean, I think we have a lot of time to go into the technical details. Okay. But I have the slides. So if you have some doubts, we can even go a bit deeper into the methodology. So the outline here is very brief in the sense that I'm trying, as I said, to match what is distributed fault diagnosis, the context of that, and especially within the framework of large-scale network systems like the application I'm going to present. And I will try to match it with the digital twin concept, which is now a buzzword that is used a lot. But I would like to make the point of how a digital twin should be designed in order to be actually useful in a practical case when you have an actual plant that is not an academic system of 2 or 3 state variables, okay? And then you have completely different framework to work with. Okay, I think I can skip this slide, okay? This is just providing the motivations of why the problem is important, especially for the industry, the problem of diagnosing faults, abnormal behaviors, and the reason is that you want to actually achieve safety, performance, reliability. And it's important to understand that faults not necessarily means a failure of something, okay? So a fault is a more general, let's say, definition, as I'm going to explain in the next slide, but it can be even off-specification production in some case, okay? And one of the things that I'm going to show you in the practical application, but I don't have the time in this lecture to go into the details, is what you do when you detect that something has gone wrong. What is a corrective action that you could do? And that is something that I will show in the application. Okay, just to set the scene, a few basic definitions, okay? As I said already, a fault is just an undesired change in the system, okay? That does not necessarily mean that there is a failure of a physical component. And when we speak about fault detection, okay, fault detection is just a binary decision, okay, to decide whether something has gone wrong or everything is fine, okay? If you go deeper then, okay, if you go beyond just detection, fault isolation is to determine or learn the source of type of the fault. So after you detect that something has gone wrong, you want to try to locate it where the problem is in your distributed system. And when we speak about fault diagnosis, it's the entire procedure of detecting, isolating, possibly even evaluating and quantify the problem that has occurred. Okay, and what is digital twin? Well, digital twin, if you Google that, if you Google the buzzword, digital twin has not a common definition, okay? And therefore here, I would like to make it specific, okay? And I would like to explain what digital twin for me is and in my application, okay? Is a digital copy of the plant, not of the controller, okay? And the idea, which is quite obvious, is that you basically consider the plant and you replace the plant with a copy of it, where that means that you have a big simulator. However, the simulator should be connected in hard real time with a true automation system. Okay, so here is where you have PLCs, where you have all this kind of control hardware. Okay, and the input and output should go in the real time, hard real time. Okay, so that you basically unplug the automation and plug it to the simulator. Okay, that is the idea. And for what we are concerned, we typically do not need most of the time that this simulator is very accurate from a mathematical point of view. What has to be accurate is the way it interacts with the control. That is what we care about, okay? And I will go into the detail later on. Okay, and then the other thing I would like to make here is that to understand clearly what we mean by distributed, okay? Because that is the monitoring framework that I'm going to deal with here, okay? So suppose that you have a big system, okay? This is just a picture, okay? It can be a large-scale system like an industry, a power, a critical infrastructure, and so on. And clearly you have many parts here, as you well know, that are dynamically coupled, okay? Then, what is the idea? The idea is that you basically associate with this large-scale system, for example, our industrial plant that I'm going to deal with later, okay, with a graph, okay, very standard, old-fashioned representation of a dynamic system. And suppose that eventually a fault is occurring in one of these subsystems, okay? And it's detected. Okay, so you detect that there is a problem and you locate it somewhere. In this case, for example, in this subsystem here. Then what you want to do? Well, you want to avoid the propagation of the problem. That is the main objective, okay? And therefore, that typically happens by unplugging the system, okay, without spoiling, for example, the stability of what remains. That is important. And in general, it's not true in a general system, as you well know, that if you unplug a part, you might spoil the stability. And you don't want to redesign the whole control system because you unplug the part of it. Okay? And the other way around, okay, once you solve the problem and you want to replug back the controller, again, the subsystem, again, you do not want to redesign the entire system. You do not want, when you plug it back, to again spoil some of the important performance metrics, and possibly you have just to redesign some local controllers, okay? So that is the reason why we work in this way, and eventually you can get to a complete fault-tolerant control solution. I'm not going to the control in this talk, okay? But the important point I want to make is that there is a solution we already developed here, kind of a plug-and-play solution, where the key point that we have developed in one of my not very recent paper now is the fact that you can really build something that is plug-and-play, okay? But the key point is that the way you decompose the system into subsystem, in general, differs. The monitoring part and the control part have a different decomposition. They do not need to have the same, okay? And this is dealt with in this paper. Here, I'm going to connect the digital twin solution with just the first part, with the distributed network fault detection, and this is what I'm going to talk from now on. Okay, let me first try to focus on what we mean by distributed here, okay? Something very classical, actually. First of all, why? Why do we want to distribute the task of monitoring? Well, there are a number of good reasons, okay? First of all, distributed because the computation power requirement, of course, the communication resources as well, okay? And last but not least, a fault diagnosis procedure that is only located in a centralized way is not per se fault tolerant, right? So if you can distribute that, you can inherently plug in also some more resiliency in what you do. So there are good reasons why we want to distribute it. And why networked? Well, networked is a concept that in the industry is now ramping up a lot, because you want more and more to put intelligence into the single components, okay? Now you have intelligent actuators, you have intelligent sensors, and so on and so forth, where computation can be done locally, okay? So this is something that is also very consistent with the industry 4.0, now is going to be 5.0, whatever, okay? Okay, so what is the difference for us between decentralized, centralized, and distributed? Well, centralized is quite clear, okay? Everything is interconnected, dynamically interacting in a big system, okay? With a possible very large number of components. Decentralized is the other way around, okay? We well know how when we design a, let's say, decentralized control system, we have many controllers distributed, and we assume they don't interact with each other, and the interaction is just seen as a disturbance, okay? So that means that there is no information exchange between the subsystem. Distributed means that we are kind of being in the middle between these two extremes. That means that you do have a decentralization, but you have information sharing between local subsystems, okay? They can interact with each other, but only locally. It's kind of a middle way between the two. And this is what we are going to deal with here, okay? And the first thing we do is that when we consider the fault diagnosis architecture, we want to develop a distributed one, we want to develop it in a way that you basically mirror in your distributed fault diagnosis scheme the interaction and the exchange of information. So if you have a graph of interaction of information exchange, you kind of mirror that when you distribute the fault diagnosis scheme, okay? This is the way we go. And let me, before we go to this slide, I will go back to that. Let me make an example of what I mean, okay? Just to fix idea, okay? So suppose that you represent a dynamic system, the big one, in the usual way with a structured graph. I think this goes back to the 70s, okay? 1970s, I think, this way of representing dynamic system as a structural graph, okay? Where nodes represent state and inputs, okay? And two nodes are interconnected if one node appears in the state equation of another one, okay? It's a very natural way of representing a dynamic system as a structural graph where you have nodes and you have arcs, okay, with a clear meaning, okay? If you have an arc between xi and xj, that means that xi acts on xj, okay? No more than that. Okay, that is the big system, the monolithic system, okay? And suppose that then you decompose it, in this simple example, I'm decomposing in two subsystems, okay? And see what that means. It means that here I have subsystem S1, and the definition, what we call local state variables, is quite obvious, okay, are the states that are comprised in this rectangle here, and the same here. And here you see that you might have truly local state variables, that means that appear in one of the boxes and not in the other, but you might have shared variables as well. So they appear in the intersection of the decomposition. Okay, so for example, in this case, you see that X3 is in the intersection. Okay, so in the overlap set O3, that means that subsystem 1 and 2 share the state variable. That's just a notation. Okay, but this just to say that the way in which you decompose the big system matters here, matters quite a lot. Okay, and there is a whole research area, it's an open problem of what is the optimal way to decompose a big system, okay? And it's an open problem, it's a very difficult one. I'm not presenting any solution here. I have some papers, but very hard to prove something in that respect. Let me go back to the slide that I skipped, okay? And here are the main part that I want to here highlight a little bit, okay? I already dealt with the 3 bullet points here, the fourth and the fifth are important as well. When you are having parts that are shared, okay, you want to take advantage of that. Because if you have overlapping part, it may well happen, for example, that on subsystem S1, suppose the example I showed before, the uncertainty that you have, for example, in estimating state X3 might be much larger than what you have on the other decomposition. And therefore, we are going to embed in the methodology kind of consensus techniques so that we take advantage of the fact that kind of two systems look at the same variable. And if one has much less uncertainty, we can take an advantage of that. And the other thing we are doing here is that we want to, by means of an adaptive approximation scheme, to learn where the uncertainty is, at least a little bit. And the typical thing that we want to learn is the dynamic interconnection, because how a subsystem is actually dynamically influencing the other subsystem. And we develop an adaptive approximation scheme that is able, under some assumptions, of course, to learn at least a bit of the uncertain part. Okay. Slowly, I'm going a little bit into the details of the formulation, okay? Suppose that you represent your big system, what I call the monolithic system, the giant, okay, in this way. It's just a way to formulate a problem. There are more general equations that we can build up, but for the sake of explanation, I think this is enough here. Okay. How is this state equation, the big one, generally composed? Is composed of a nominal model dynamics. A nominal model dynamics is what you know about your system, okay? And that represents the dynamic behavior in healthy conditions, okay? When you are sure there is nothing that went wrong, okay? That is the nominal part. Then you have an uncertainty, okay? You have something that takes care of the fact that, of course, the nominal is not exactly coincident with the true dynamics, okay? And that is what represents the plant model mismatch, the blue part, okay? You might, of course, have uncertainty on the measurements. Now, for the sake of simplicity, I just wrote it just as an additional disturbance, but you might have more complicated equation here as well. And then the red part is what represents the fault, okay? So the fault typically is represented in this way, where you kind of separate what is the time evolution of the fault, abrupt or incipient. In the case of the abrupt fault, what we don't know is when the fault has occurred. In the case of an incipient time profile, then you might also not know the rate of evolution, okay, of the incipient fault, okay? That is another unknown in our problem. And we typically separate that component by this vector field F that instead is representing how the fault is actually affecting the dynamics, okay? Is the deviation to the state equation due to a fault, okay? Of course, you might not know this F. And this is, for example, the case where once your system detects that there is a fault, then you might turn on your adaptive approximation scheme that tries to learn at least a little bit of that, okay? Okay. How we decompose that? Well, if you remember what we have seen before, okay, we consider a decomposition of the big system into subsystems. And then for each of the subsystems, you might have an equation like that. What is this equation representing? Well, first of all, the nominal local dynamics, okay? Then you have this blue part here is not only including the modeling uncertainty as before, but of course it's also including the interconnection dynamics. So how the other subsystems are actually influencing the dynamics of your local subsystem. And in general, you cannot separate these two, okay? They mix together in some unknown way, okay? But clearly this blue part is there here. And the local measurement uncertainty, of course. And here, this red part is a little bit more complicated than before, because now what you represent here is the influence of the fault on your local subsystem, which might only be a part of the dynamic influence of the fault, of course, okay? And let me explain what I mean, okay, by an example. So here we are, what I'm going to say is that we have two kinds of faults, okay? Faults that only affect your system locally. When you say locally, I mean locally by the decomposition that you have considered, okay? So for example, here, if these state variables are actually impacted by the fault, that fault is only local, okay? The influence set here is a singleton, okay? And that has an important implication, because that means that if you associate with S1 one piece of your monitoring, distributed monitoring system, that means that that piece of monitoring subsystem is able actually to detect this fault under some condition without necessarily have nothing to do with the other subsystems, okay? That is, in a way, is a very simple fault, okay, in our scheme. But clearly, faults might be distributed instead. So a fault might affect state variables that belong to kind of affect shared part here. And for example, in this case, you see that the fault is going to affect a number of state variables that cross the boundaries of two subsystems here, okay? And that has an important implication, because in this case, if you have designed a fault isolation component, which means something, and I will go to show that later, okay, that not only detects that there is a problem, but is also able to locate where the problem is, that isolation part in this case is possible. But in this case, it's not. In the sense that in this case, if you want to locate, isolate the fault, the isolation procedure necessarily will need that the fault diagnosis unit 2 and 3 communicate to each other. Otherwise, there is no way you can kind of associate where the fault is to one subsystem or the other, or both, okay? That means that the global isolation strategy is needed, and that is the motivation for the architecture we propose. And the architecture we propose is the following, which is kind of obvious in a way. So we have 3 layers. That is our main proposal, and let me explain a little bit that. And that has an important, not only impact, I would say that this subdivision in 3 layers is coming to our proposal exactly because we were influenced and inspired by the real application. So what happens in an industrial control system is that you typically have layered automation system, okay? We well know that, okay? And therefore, we propose that there are 3 layers. Let me call layer 0 the physical layer, okay? Physical layer means that you have physical subsystems, okay? And the variables of these subsystems are measured by independent and local sensors, okay? You might even have a local sensor network. Local means that in this sensor network, everything is synchronized, okay? But not necessarily synchronized with the other sensor networks. They might be even very far away. And there might be no need to actually synchronize everything on the single clock. Typically, that is not done, okay, in a plant-wide automation system, okay? So that means that you can think of these sensor network to stay in their own, let's say, life, okay? They are synchronized locally, but not necessarily with the others, okay? That means that now you need a second layer, layer 1, okay, where you have your local fault diagnosis units, okay? What are those doing? They acquire the measurement each of one needs from one or more sensor network, okay? And that means that you have this layer here where you have, in this case, I have 3 subsystems. So I have 3 local diagnosis units, okay? And you see that these units are getting information from more than one sensor network. And that means that these units here okay, are getting this information in an asynchronous way, okay? And the only way they can kind of then match everything together in order to take global decision is that they have to communicate with each other. And that is the third layer in a way, where these units exchange information between each other in order, for example, to do the synchronization. Because if you don't do the synchronization, you cannot hope, for example, to have timestamps that allow you to kind of making the information that you get coherent. And if it's not coherent, how can you hope to make a good diagnosis decision, okay? And that are, in a more precise way, all what I said, okay? So here you see that you have local synchronous and you need the synchronization, okay? And here is the first point where digital twin come into the picture, okay? Let me explain why. Because basically the way you do it, that is very standard, for example, in distributed model predictive control, right? Where you have your virtual stamps, okay? And you try to synchronize them, but how can you do that in practice? Well, you do it by what is called virtual sensors, okay? So basically virtual sensor means that you are kind of using the knowledge of the local dynamics in order to project what the sensor information could be in the future. And that is the synchronization to get to a common timestamp, okay? And this is what I mean, okay? So basically you have what you call virtual sensor, but the virtual sensor is no more than using the dynamics here, and that is where the digital twin is coming into the picture. You use the information of the local dynamics to actually project in the future to synchronize with the others, okay, and getting this virtual timestamp here. But how can you do that if you have not a model of the dynamics that runs in real time in parallel with your plant? That is what we have done, okay? Then, of course, we can go a little bit, just a little bit into the details concerning locally how you solve the problem. Well, the structure that you have, and here again, this is generated by your digital twin, okay, this equation here. Now it's in discrete time because now you have the timestamp and you synchronize everything virtually. So this is actually the digital twin execution in real time. And the structure that is well known, okay, so this is now classic, I have to say, from the early 2000. You basically have two elements here. First, you have a fault detection and approximation estimator. I'm shortly showing what I mean by this, that takes care of detecting that something has gone wrong locally. Okay, and therefore, if something happens, you raise an alarm. Okay, something has happened. Remember, binary decision. It's okay or it's not. And that triggers, activate another procedure that tries to match the dynamics, the faulty dynamics that now you have with some priori knowledge that you might have. That is an important point that I would like to make shortly, okay, because sometimes there is a little bit of misunderstanding here in the literature about that. But basically, the green part here is trying to decide what fault has occurred in that local subsystem, if any. Of course, it doesn't mean that you ever are successful in this. It might be that you raise an alarm, but you are not able to tell what the fault has been. And at that point, it's a decision by the plant operators what to do, okay? Okay, I said that already. Just a little bit on the details, how we do that, okay? So let me first focus on the black part, the fault detection and approximation scheme. So basically, it's a nonlinear observer, let me say in a very sloppy way, okay? It's a nonlinear observer that is using the local dynamics information, that is the digital twin that gives that in real time. But then it has, you don't see, this is a dark red, but this is basically where you learn what has gone wrong, what went wrong. Because clearly this part here, the red one, is a nonlinear adaptive approximation scheme, which, by the way, uses neural networks in this case. They work very well for this task. But you see that when the system is in healthy condition, this is 0. Okay, so this is only activated after there is a detection of a fault. Okay, that is important. Okay. Well, this is one of the typical structure you could use in the practical application I'm showing. I'm using a standard kernel-based approximation structure here, but you can use many others, okay? That is not a problem nowadays. Okay, and how is the learning algorithm designed? Well, the learning algorithm is rather standard, in the adaptive online approximation literature. So basically you have an adaptive mechanism here, okay, that is based, of course, on kind of a prediction error scheme, but then you need also some kind of projection operator to avoid parameters drift. We are not assuming persistency of excitation here. Everything is nonlinear. So then you typically need anyway to have kind of a projection operator, and then there are usual mechanisms in order to decide what the learning rate should be or not, okay? It's quite a standard scheme here, and you can find the details in one of the papers that are in the presentation that, by the way, I will share. Okay, what we mean by local fault detection. Let me explain how the logic works, okay? Clearly here, since you have uncertainty, you need to have an estimate of the modeling uncertainty, an estimate of a bound on that. Otherwise, how can you decide? Okay, so that means that the real challenge is when the faults are very small. Okay, when the faults are slowly developing, that is a much more difficult problem to solve, but there is nothing else you can do. Okay, unless you assume persistency of excitation and geometric decoupling between fault and dynamics, there is no other way you can solve the problem. And imposing geometric decoupling between dynamics and fault is something that in practice you can never do. Okay, it's not practically viable. Okay, so the only thing you can do is to use kind of a bound on the modeling uncertainty, and then the decision is clear. Okay, you generate your residual over time. At some point, you might have a fault, and what we have shown in our paper is that there are no false alarm in our scheme. Okay. It might be conservative, so you might not be able to detect some faults, of course, but if you detect a fault, you are sure there was one, okay, by the way we have developed the theory, okay? And so that's quite an easy decision scheme. And when you go then to activate the isolation part, then that is the point I promised to make, okay? If you want to decide which fault has occurred, is basically a model matching problem. What do I mean by that? I mean that suppose that I have a valve, a pump, and a sensor, okay? If I don't know how the dynamics of these faults are kind of influence the total dynamics, how can I distinguish between the two? So that means, in other terms, that in order to solve the fault isolation problem, you need to have kind of a library, okay, of association between a physical fault and what's the effect of that is, okay? So you have that library, and you try to match with that library in a scheme that I'm showing now, okay? But of course, if you are not able to associate the effect of the fault to any of those, then you give up, okay? You say, okay, there is a fault, I'm not able to tell, okay? And the interesting thing is that, again, we have shown that there are no false isolation decisions. Of course, you might miss to isolate false, but there are no false alarm in a way again. And the way the logic is working is quite simple. Okay, suppose that you have, this is just an example to show what I mean. Suppose that you have just 3 false types that you are interested in. Okay, then you have one estimator for each of these kind of faults. Okay, they run in parallel. Okay, and if eventually at some point, you see, at some point you cross the threshold for the type number 2, that means that you exclude that because there is no model matching with the type number 2. Okay, and if you are lucky enough that you go to a situation where you can also exclude the other one, then at that point, at time instant 3, you have only 2 situations. Either the fault is number 1 or it's a fault that you don't know. Okay, and that is how the logic actually works. And again, it was proved that there are no false decisions here. Okay, maybe we skip that. So these slides is only shows how the estimator is done for each of those type of fault. Is a model matching problem. Clearly here, the only point I want to observe is that this adaptive structure trying to match the fault is simpler because now you know the kind of function you want to match with. Therefore, there is nothing to learn here. It's only to estimate the magnitude of that, okay? But it's not like when you don't know which fault has occurred, because in that case, you have to learn it, okay? In this case, there is nothing to learn. It's just to match the fault with the class you know. Okay, and now let me go to the digital twin. So how do they get into the picture? I already said that a bit before, but basically, every time that you have a function, a dynamics that you need to simulate in parallel with the plant, then this is the goal of this is what the job that the digital twin does for you, okay? And let me now go into the details of that. So this is a typical picture. Okay, now the application I'm working on since quite a lot is metal industry. Okay, I work quite a lot in that area. Okay, and this is the part where the digital twin is. This is a picture that you can Google, okay, from Industries 4.0 for that kind of plant. Okay, so now the industries, the process plant are having all this kind of stuff, okay? They have a plant monitoring, predictive maintenance, all these kind of things. Okay, the digital twin is coming here. It's a simulation, as I said many times now, that runs in parallel in real time connected with automation of the plant, okay? Okay, I already explained that. I would like only to say that, and that might be interesting for any of you that is not interested at all in fault diagnosis, but you might interest what is digital twin helping with in the industry? Well, not only to diagnose faults that I'm going to show, but also because before plugging your automation system to the plant, which is, they call it commission, the automation system. Okay, if you have a digital twin, of course, you can do virtual commissioning, okay? You can commission the automation on the digital twin and then bring it to the real plant and plug it in, okay? And there is an estimate in this kind of industry that the commissioning of an entire automation system of a steel plant, for example, takes typically between 3 and 6 months on site, okay? We have shown that it can be reduced to 2 weeks, okay? Basically, you do it in-house, so you don't need to bring 30 people on the plant somewhere in the world. You do it in-house. There was basically a container with automation system connected with a digital twin. You correct all the bugs, you resolve all this problem, okay? Then it is shipped, you plug it, okay? And in 2 weeks, it was working, okay? I will show some result shortly. But not only that, okay? The third bullet point is even more important. expert plant operators are less and less available nowadays, okay? But if you have this kind of tool, you can even use it to train the operators, okay? Like a computer game, right? In a way, but you can use it for that. Okay, let me skip that. So this slide has only the goal of showing you that if you want to make a digital twin of a process plant like that, there are many things that you have to consider in your big model, okay? Going to our common buzzwords, okay? You have a lot of physical processes, and then you have continuous discrete PDEs. You have all these kind of things, and you have a lot of many scheduling discrete event parts, okay? All these have to be considered. Okay, let me skip that, okay? Okay, what are the challenges? So what should you prepare? Suppose that some of you get a contract with an industry, okay? And they want to give you money, research money and innovation money, whatever, to develop a digital twin for their plant, okay? I don't know. Saab is willing to do a digital twin of their manufacturing plant, for example, okay? What are the challenges? Well, first of all, it's not only a kinematic simulator, okay? It's not only a simulator that simulates the movement of pieces, okay? The more important thing most of the time in manufacturing is that you need to model and simulate the interaction of the material that you produce, of the object that you produce with a machine. This is typically not accounted for. Next, if you go to your funder, your industry, and you say, okay, yes, we can do it. Give us 2 years and we do it. They say goodbye, okay? They cannot do that with so much time, okay? Therefore, what you have to develop is kind of an automatic creation of that model based on the plant layout, on the functional specification, on the list of the IOs, and so on and so forth, okay? Next, reparameterize on the fly. You do one digital twin, they are very happy, then they say, okay, can you make another one for this other plant, okay? Similar, but not the same. You want to be able to reparameterize that on the fly, okay? So you need to make sure that this is possible, okay? And last but not least, mathematically speaking, you need to be able to embed standard, simple models of actuator sensor with, for example, very complicated distributed parameter equations, okay? For example, as I'm going to show, when you model, for example, a rolling mill, okay, the way the rolls are actually interacting with a steel plate, okay, that has a temperature around 600 to 800 degrees, it's a very complicated mechanical interaction, but they are very interested in that because they want to see the properties of the material, because the property of the materials are important when you produce them. Okay, so in our case, what we have done something like this, okay? So we have basically 3 main elements here. The first one is that we constructed a procedure to develop PDEs models that are amenable to be implemented in real time, okay? So that is basically using real-time approximation that are good enough, but solving the compromise with the real-time execution of that. Second, you need to have an automatic construction of the IO. We are using MATLAB Simulink, okay? So that is, from that perspective, that is standard. However, they give you the 3,000-4,000 IO variables in an Excel spreadsheet. You need to automatically create all the input-output blocks, okay? You cannot do it by hand. That has been solved. But last but not least, you need to have, let's say, a target operating system, and that is where the IP is, that is actually able to run in real time. Here we are running 1 millisecond hard real time and the entire model, okay? Well, okay. This is the holistic view, let me say. Okay, so basically the red arrows here is the information that you have that is basically written in files, okay, that you need to kind of parse and extract the information you need. For example, the specs of the machine, the data characteristic, the reconfiguration and setup of the automation, okay? And then what is inside this rectangle is actually the digital twin, okay? So where you have all the components, in this case, we are talking about the mechanical plant system, and of course, the topology, okay? All what is in here is automatically generated from the red arrows here, okay? And what is inside this rectangle is going to take the actuation inputs. Remember that the digital twin is the plant, okay? So the input are the outputs of the controller, and the outputs are the predicted outputs of the sensors, okay? This is the loop that works, okay? And the outputs that then you get on a higher level of abstraction are, for example, a comparison that with a factory acceptance test, okay? And basically, this is the automation structure of a typical plant, where here you have the physical component, and your digital twin has to basically to replace the physical part with some computers that are connected in real time that run your digital twin. Okay, so I hope I gave you the big picture. This acronym, I hope you remember what it is, hardware in the loop. Okay, when I write HIL, this is what I mean. Okay, this is just a snapshot what I mean when I said automatic generator, and then I will move on with some videos and some actual result. Okay, so you basically get that. This is an example where the automation is implemented on Siemens PLCs, but you might have other kind of hardware where you run your automation. And you have an Excel file, a very abstract, not understandable, where you have these names of the variables, you have the specific memory part where these variables are located and so on. And you basically have to parse that file and automatically generate the inputs and the output, okay? That is what has been done. And this is what enables you to reparameterize on the fly. If you add a sensor, you add an actuator, you just have the file modified by that, and you rerun the parsing, and you have your additional block that you need, okay? Maybe I skip that. That is something I can talk offline about how you build these numerical models, okay? And that is just a compilation target. Okay, let me now go over some result, okay? So that is an actual implementation that has been delivered already. Okay, so here you have the computer, the monitors that are getting you the information about all the variables that you are having here. That is interesting because that means that if you have a model that runs in real time, you can also look at the internal variables that might be interesting. For example, these internal variables might have the stress and the strain of your material while it's rolled. This is not something you can measure in real time at 800 degrees of temperature, right? But if you have an accurate model that in real time is telling you, the plant operator can see what are the internal stresses, of course, approximate internal stresses, the profile of that, whether there are non-uniform temperature, and so on and so forth. That is the digital twin part. This is the automation system. You see, this is the rack that has 12 PLCs, I think 1,500 Siemens PLCs, that are only for the roller table part. So the final part after the strips get out from the rolling mill and it's coiled, okay? And this is the actual control pulpit. This is the one that goes on the plant. So where the operator is actually interacting with the plant, okay? Everything has to be connected. Okay, so this part here and this part here are the one that goes to the actual plant. This part here is the digital part, okay? Okay, and now, I hope the animation works. Okay, let me show what we have here. So this is an actual how to say, representation. So here is what you see on the internal variables that your digital twin is providing to you. This image here, you see that is blinking, so this is working here, is the actual HMI, human machine interface, that the plant operator is going to use on the plant, okay, which is of course connected with the digital twin. And this is a rendering, a 3D rendering that is showing what is going on in a virtual way, okay? And notice that this digital rendering here of the actual plant part that you are focusing, and I show something else shortly, is also automatically generated. So you're not doing manually. You take the drawing, okay, the electronic drawing of the mechanical part, you parse them, and you automatically create the dynamic pieces of that, okay? And this is also actuated in real time. Okay, here is another that maybe shows you more what is going on, okay? So here, in this case, you have a touch screen that is actually, I cannot stop that. You see that here you have a fault. You have seen there was an imperfection in the strip, okay? The imperfection was due to the fact that there was an uneven pressure in one of the two pistons of the rod, okay? And so that was creating this imperfect profile of the strip, okay? And here, that part here is exactly what you have seen before. So this is the actual HMI, and this is the rendering that you have. Okay, here is another example that is showing, again, this is driven by the digital twin in real time. So you have the automation that is running, and here is what is kind of generated. And this is why I'm saying that this is useful for plant operator training as well. Okay, let me show you something different, and then I show also some other interesting movies. Okay, of course, if I'm going to try to convince you that the story is finished here, of course it's not, okay? So you develop your digital twin, but then the digital twin has to be calibrated on the real plant, okay? Because otherwise, of course, there are always little difference here and there, okay? The calibration is very important. And here, for example, I'm showing you the calibration of one piece of the digital twin, which is the looper, okay? The looper, you will see a movie shortly about that, but I hope that is starting now. So the looper is this element here. So it's the one that kind of keeps the tension of your strip, okay? So make sure that there is always enough tension, and you have to calibrate that. Calibration means that you have to calibrate the parameters so that a given displacement corresponds to a given force and a reaction force of the strip, okay? And the calibration works, I don't know whether you see this, you see that this is moving. You move it at different level, okay? And this corresponds to these steps here, okay? What you have on the right is the real plant, okay? So this is the real calibration, and this is what the digital twin is giving you. So you have to calibrate the digital twin in such a way that then perfectly match what is happening in the real plant, okay? So that then you can actually use it. And here you see that the movements are a little movement and a bit more, then a bit more, then a bit more. You do it on the real plant, you do it on the digital twin, and you match the two, okay? Okay, so when everything is working, okay, this is what your digital twin gives us. Here I'm focusing on the rolling mill part. Of course, here I removed from the drawings some details in order to see what's going on. I hope that they are not synchronized, okay? I was not able to synchronize the two things. I'm not good in these things, but I hope this is moving eventually. No, maybe this didn't start, sorry. I had to start, oh yes, now it's moving, okay? So let me then, if I click that, no, I didn't want to do that, sorry. Yeah, move back, move back. Yes, I should have 20 years less to do these things. The animation is always a trouble for me, okay? But this is moving, so I hope at some point you will see the strip coming, I hope. Let's wait a bit. I want to see that. Yes, it's coming now, okay? So this is when the new strip gets in, okay? And here you see that I remove a lot of the mechanical part around to see what's going on internally, okay? And you see that here is the first looper, okay, that stays down. And once you enter the next rolling stand, then eventually you see it went up to create tension, okay? And so on and so forth, okay? This is exactly what is done here. But if I now click again, I will move to the next slide. Sorry about that, okay? That is when no faults is there, okay? But let me now show what happens when there is a fault. Okay, here a fault is a cable, okay? And let me wait to see. That is on the roller table after it gets out from the rolling mill. And notice that the colors are representing the temperature. Here, the temperature of the extremes are typically higher, and here is the cooling mechanism. Also, the cooling is simulated, okay, here. And at some point, I'm not able to accelerate that with this pointer, but at some point you will see that a problem will occur, okay? And when I click, you will also see the problem in the real case, okay? Yes, it should come at some point. Sorry, thanks for your patience. Okay, you see a cobble here, okay? And if I now click, you see a real cobble. And also you are going to see that is a real cobble, okay, that is happening, okay, it's exactly this kind of phenomenon. But with the digital twin, you are able to predict that. And then here you see that is the recovery, okay? So once there is a cobble, you try to recover. And here you see the digital twin is telling you how you can recover, how much you have to increase or decrease the speed of the coiler in order to recover for the cable, okay? And that was very useful for us to tune the controller that automatically does the recovery in an automatic way, okay? Because of course, that phenomenon is very bad if you don't. And here there are, okay, other simulations, but I think we ran out of time. But I will give you the presentation. I will ask you not to keep it internally, not to put that, these movies are not, I'm not intended to kind of put it on Facebook, okay? That is not the case. Okay, what are the, okay, that is the previous project. So what are the takeaways, okay? Well, I hope that the reasons for this to be good and useful, and the reason why when you speak about digital twin, everybody is listening to you, is because it's getting important. It's getting important in several situations. I think Professor Policarpo made, we have a project together, made a presentation where he was showing the smart city thing, okay? So also in that case, a digital twin of a smart city follows the same concept, okay? In their case, they took, for example, the topology of the city, the topology of the water network, okay, the topology of the traffic system, and they automatically use that to make an instance of the digital twin of that specific city, but the concept is the same, okay? And the concept of having models generated automatically in real time is the same. Of course, when you talk about an industrial control system, the requirements are a bit different, okay? But I think the concept is the same. And the fact that you can use that to solve fault diagnosis problem is important. And why it is important? For two reasons. First, when you go to a company and you want to solve their problem, they will never give you data about faults. They don't want to show that they have faults. Okay? So that means that data representing faulty situations are very rare. Okay? Very rarely you get them. Okay? And therefore, this is why having a digital twin that is high fidelity can help you to generate those situations. And then you generate the data. And by the way, if you want to build a machine learning system that tries to understand and builds the model from the data, you will never be able to do it on real data because they are all flat. Everything is working fine. So what are you going to learn from that? Okay? And that is an aspect that is, in my opinion, also there are people that do a lot of system identification in this university. That is exactly the same problem, okay? Having a way to generate synthetic data that are representative of rare events, okay? And that is something that in practice can be useful. I think I already went 3 minutes more, and but I will stay here, okay, for a few weeks now and in September, so I will be more than happy to talk about these and other things, okay? And thank you for your attention.